part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to continue the discussion of magnetic materials. In particular, we'll consider linear materials, and then we'll also derive the boundary conditions, and then apply those boundary conditions to certain kinds of problems, or I should say 3 different examples. Last time, we introduced the H vector, the auxiliary field. And that's equal to magnetic field B over mu naught, permeability of free space, minus magnetization. And then we also derived Amperes Law, which tells us, again, the line integral of the auxiliary field around a closed path is equal to the amount of free current, or current that involves the transport of charge through that loop. Okay? What I mean by linear media is that the magnetization is proportional to the H field. And notice I'm defining it with respect to the H field and not in terms of the magnetic field. That is by convention. If you recall back to dielectrics, we defined the polarization as the susceptibility times the electric field. It wasn't in terms of the displacement. So as I said, this is by convention. And for linear materials, this susceptibility is just a number. And so what do I mean, or what kinds of magnetism fall under this category? Well, diamagnetic materials and paramagnetic materials can be treated this way. Diamagnetism, as you'll recall, means that the moments tend to oppose the applied magnetic field. Paramagnetism, the moments align with the magnetic field. So therefore, in the case of diamagnetism, the susceptibility is negative. In the case of paramagnetism, the susceptibility is positive. Now, the order of magnitude of the susceptibility, which is much, much less than 1, typically talking about values around the range of 10 to the minus 5. So that's what I mean by a linear material. Notice I didn't mention ferromagnetism. Ferromagnetism is most emphatically not linear. Life becomes a great deal more complicated if you want to analyze the ferromagnetic materials. And I'll defer, again, a discussion of diamagnetism, paramagnetism, ferromagnetism, flesh it out a little bit more in an upcoming lecture. But for now, the kinds of substances that you could treat using this relation, or you can model using this relation: diamagnetic, paramagnetic, absolutely not ferromagnetic substances. Okay? Now let me just rewrite the magnetic field, B. And that's equal to the permeability times the H field, and plus permeability of free space times magnetization vectors. I'm going to substitute in this expression, which holds for linear materials. These taken together is just the permeability of the material. let's apply this to a problem. Let's suppose that we have a solenoid. And it's very tightly wound, it's very long, and we'll assume, just as we did before when we were just calculating the magnetic field, that there is no longitudinal component to the current. The current's just in a circumferential direction. So the same argument that we used to determine the magnetic field B before, we can use that again to determine what H is. So now, instead of having an air core, let's say that we've got some substance that has susceptibility chi m, and I'm going to figure out what's the magnetic field everywhere. Well, applying this, we'll see that H is equal to number of turns per unit length times the amount of current that's carried by the wire that's wrapped, or that makes up the solenoid. And it's in a circumferential direction. And this is inside, outside, magnetic field vanishes. So let me just draw another solenoid here. We've got wires wrapped around it, but I'm not going to draw it in because you won't be able to see. This Amperian loop, recall, for solenoids you want to draw a rectangularly shaped Amperian loop, and remember we argued or reasoned that the magnetic field had to vanish outside, and there was only one component inside, or one leg of this was non-zero, and that was because of the surface current density, which we could say was equal to Ni. Okay, but the magnetic field now inside is equal to mu times H, because we are assuming that this is linear material or linear matter that's inside the solenoid, and that's equal to mu naught 1 plus chi m times H inside and outside. B is still equal to 0. Okay. Now let's move on to boundary conditions. Two equations that govern the magnetic field are, number one, the divergence of the magnetic field vanishes, and in fact that's always the case, and number two, in magnetostatics, the curl of the magnetic field is proportional to the volume current density. We showed before that these two equations imply the following boundary conditions. And number one, the divergence of the magnetic field implies that the normal component of the magnetic field is continuous across the boundary. And number two, the fact that the curl of the magnetic field is proportional to the current implies that the tangential component of the magnetic field suffers a discontinuity at the surface or the interface, and that's equal to mu naught times the surface current crossed into the normal component. Let's write down what the boundary conditions are on the H field. After all, it'll be more convenient to express it in H since we are dealing with magnetic materials. So first of all, let's consider H. Let's write H in terms of B. And if I take the divergence of both sides, this expression. So the divergence of the magnetic field always vanishes, but that isn't the case with the divergence of the H field. You see that the divergence of the H field is in fact equal to minus the divergence of the magnetization. The only case where this side vanishes is if the divergence of the magnetization also vanishes. So that's a big difference between the H field and the B field. And that leads to correspondingly different boundary condition. Therefore, the normal component of the H field suffers a discontinuity, and that discontinuity is equal to minus the discontinuity in the magnetization. Let's consider, what about the curl of H now? Curl of H is just equal to the free falling current density. If I compare this expression with this curl, I can just basically derive automatically, or write down automatically, the boundary condition in the tangential direction. So therefore, the discontinuity and the tangential component of the H field is equal to the free surface current density crossed into N. Let's consider what happens if you don't have any free current. So if there's no free current, JF is equal to 0. And therefore, curl of H is equal to 0. Back in electrostatics, one of the governing equations of electric fields was that the curl always vanished. Okay? Not so in time-varying fields, but in statics, curl of E equals 0. So in that case, we were able to deduce that there existed some potential such that its gradient was equal to the electric field. So that's what I'm going to do here. If the curl of a vector vanishes, I know that I can write that vector as the gradient of some scalar function. And just as before, we said that the electric field was equal to minus the potential. Here, we'll say that the H field is equal to minus the gradient of this quantity here. Which we'll call the magnetic scalar potential. Okay? Well, where's that getting us so far? Well, if there are a couple of conditions satisfied, we can wind up with a boundary value problem that can be handled readily. In other words, handling a boundary value problem that can be handled using the tools we've already been using back in electrostatics. So what are those conditions? So if the divergence of the magnetization vanishes. That implies that the divergence of the H field vanishes. But because we're dealing with systems that have no free current, I can substitute this expression into here, and we'll wind up with and the divergence of a gradient is just equal to Laplacian, so therefore we can solve Laplace's equation in that case. So another type of problem that can be handled readily is if there's a simple relation between the magnetic field and the H field. In other words, B is simply proportional to H, where mu is the permeability characterizing the material in question. So in that case, it will also be true that the divergence will vanish, or rather the divergence of H will vanish. So we'll again arrive with the Laplace's equation. So when either of these conditions is satisfied, we can solve a simple boundary value problem. And by simple boundary value problem, I mean the kinds of problems that we work through in back in electrostatics. I don't mean to say imply it's easy. It's certainly not the case. But it's problems that we can solve, okay? So again, just to reiterate, boundary conditions on the H field, there's a discontinuity in the H field, generally speaking, and that's equal to minus the discontinuity in the magnetization. There's also a discontinuity in the tangential component of the H field, and that is equal to the cross product of the free current, surface current density, and the normal. And in the case that there are no free currents, in other words, where JF is equal to 0, curl of H equals 0, and therefore H can be written as the gradient of some function. And if we have these two additional conditions applying, in other words, if the divergence of the magnetization is equal to 0, or if B is simply proportional to the H field, we can arrive at Laplace's equation and use all those tools that we developed for use in electrostatic problems. Okay? So I'll leave this up here for just a bit, and then we'll move on. We've got 3 boundary value problems to solve, so I'll get to that next.